Please wait.
Hi.
So next speaker is next and the final speaker of this section is Ivan Balog. So he is going to tell us about the non-perturbative renormalization group approach to the lower critical dimension in system with discrete symmetry. So please start.
Okay. Thank you very much. Thanks for the nice introduction, and thanks for the organizers to allowing me to speak here. So let me start first by saying that this is a collaboration with Lucia, who is a PhD student, Adam Ranson, and Gilles Tajus. So, so here is the slide to thank the funding agencies, and let's get down to business. So basically what we are dealing with is our systems with discrete symmetry, and these are perfectly exemplified by the Ising model, which is in criticality equivalent to the phi to the 4 theory. So here is the Hamiltonian, which everybody knows. So spins are the discrete classical spins that can be plus or minus 1, and they interact ferromagnetically. So as a result of this, you have for large temperatures, you have a paramagnetic phase, and then at low temperatures, the system orders ferromagnetically at some finite critical temperature. And the point is that as D is dimensionality of the system is lowered, the critical temperature is also lowered. It goes to 0 as D goes to 1, which can be explained by the beautiful Parse argument, which states us that for 1D case of a short range spin chain, so there can be no ordering at any finite temperature. So this can be seen explicitly by just writing down the free energy balance that you get by introducing just a single kink. Here we see a kink and anti-kink pair. And you see that this is, there is a term which is t times logarithm of n. So it means that the kinks are entropically very preferred, and this destroys ordering. However, t equals to 0 is a non-trivial limit, and you have a diverging correlation length. And this teaches us that basically kinks are responsible for the onset of the lower critical dimension. Here, I want to point out the difference between the ON case, where for n greater than equal than 2, the Goldstone excitations are responsible for the onset of the lower critical dimension. So, but there are very few works that deal in n equal to 1 case and the approach to the lower critical dimension. Some of those works are listed here. So for example, Bruce and Wallis and Bolhausen-Berges, Wetterich, and we want to continue where those works stopped and pick up where they left off. Okay, so to just state the formalism, we use the effective average action formalism by Berges, Tetralis, and Wetterich. So here we have at our disposal an exact flow equation for the effective average action. Upon that, we use the derivative expansion approximation, which has been mentioned earlier. So it's just an expansion in low momenta. And we arrive to flow equations for functions of the derivative expansion uz, and we, as usual, use them in the dimensionless form to study scale invariant solutions. So these equations have been written at many places, amongst which also this work, so I won't go into many details. Okay, so how do we approach the lower critical dimension in the renormalization group? The answer is that the field stops rescaling in this limit. So d minus 2 plus eta goes to 0. And how to understand that? Well, just remember this simple Parse argument, where you see that basically what happens is that the ordering at any finite temperature is destroyed by having the kink perturbations, which make the field in a sense fluctuate at order 1. So this is just very similar to saying that the field in the sense of renormalization group does not renormalize. Okay, so what do we do explicitly? How do we study this problem? How do we approach it? So we start from the fixed point equation for the effective potential, and we here point out this term which is in epsilon, which is in this parameter which should go to 0 at the lower critical dimension. And we use the mathematical framework of singular perturbation theory, which is very nicely described in the book by Johnson from 2005. So what is the gist of what it's done? So we first study the epsilon 0 solution. So we drop this term and we study the epsilon 0 solution for itself. And then we play with the initial conditions of this epsilon 0 solutions such that the epsilon term can influence the solution, which means that it rises to the order at which the other terms in the rest of the equation are. Okay, so I won't go into many details because there is no time. But what we conclude, and this is one of the main points of this of our work, is that from the that this effective potential develops a boundary layer behavior around the minima, which is very non-trivial thing. So what this means is that it looks like phi minus phi minimum over the width of the boundary layer, where this width is given by this expression analytically, and it goes to 0 as epsilon goes to 0. Another thing that is a result of this strange boundary layer behavior is the location of the minimum itself, which diverges like this, and this is extremely slow divergence in epsilon. Okay, so to illustrate these results, let me show you just simple calculations that where we determine fixed points numerically in a perfectly normal way without knowing any boundary layer story. So I show you here several plots of U for D that are above the lower critical dimension, and you see this. You see that the location of the minimum spreads, but it spreads very slowly as you lower the dimension. And you also see that the behavior around minimum becomes steeper and steeper, which is also consistent with this finding. Okay, so how do you study this situation where you have this boundary layer behavior? So because of this, it is impossible to approach the limit of epsilon goes to 0 in terms of normal field, normal dimensionless field that is usually used in calculations. So this is why we use this field we call zeta, which is simply this. And to define functions inside the boundary layer. And this is what allows us analytic and numerical treatment. So how do we exemplify this? So for example, we like to study this function E, which is basically the dimensionless, the scaling function of the susceptibility. And when you calculate it in a normal way with normal fields, you get this sort of behavior. But then when you go into the boundary layer description, you get this sort of function C, which so the meaning basically the meaning of this boundary layer function C is how this tail approaches 0 in the limit of epsilon goes to 0. But now when you have this boundary layer, then you can approach this limit numerically as well as analytically. So how does it work? Well, it appears that from the boundary layer, from the existence of the boundary layer, you get very nice simplifications of the flow equations. And one of these simplifications is the fact that equation for the effective potential decouples from the derivative from the tower of the derivative expansion. So basically, this function C, which is in the boundary layer nothing more than 1 over U double prime, has this equation. And this equation to the lowest order in the boundary layer does not include any higher derivative order terms. This, of course, does not mean that LPA is exact. It just means that we have a nice decoupling going on, which allows us to treat this analytically. So eta and the critical exponents still depend on higher order derivative expansion functions. However, C, the solution for C, and thus the effective potential as well, is independent on the level of the approximation. Once you've solved it at LPA, you solved it for all cases. And also,
5 minutes.
Thank you. When you absorb this, so these C and D, they're regulator dependent constants. And when you absorb this into the field redefinition, you can find the CS implicit solution for C in canonical form, and it's this. So basically, what you see here is that it's easy to see that the physical solution requires us that this value at 0 is square root pi over 2, because this bracket needs to kill the solution for large zeta and makes it well behaved. Otherwise, it explodes because of this term. Okay, so how do we now determine the other quantities that we're interested? For example, the lower critical dimension. So we need to determine eta, which we have the equation for. And in the LPA prime case, using the Littim's regulator, it's a simple expression containing only the function C. And since we have the analytic solution for C, we can determine analytically the lower critical dimension. It's written here. However, at higher derivative order, the situation is more complicated, because we need to solve the field renormalization function Z, which also includes the contributions from the function C, and we need to resort to numerics. And here we show one such example of numerical solution, where we calculate the lower critical dimension independence of the regulator prefactor. And there are two things that are very striking about this result. One is that we have an optimum for DL at second order derivative expansion, which means that all the story about optimization of the regulator works for this case, lower critical dimension. And also another thing is that the evaluation of the lower critical dimension is 0.95, which is very close to the exact value of 1, which is quite unexpected, since eta in this since we are the derivative expansion is expected to converge fast if eta is small, but here eta is not small, eta is 1. So this is one point also that is very interesting. And I like to use my time that is left to tell you about another application of this boundary layer story, which is very interesting to us. So the question is whether there is a hysteresis transition in a 2D system. And I need to give you some background on this story, because it's a long story. So basically, what is this hysteresis transition? This is nothing more than out of equilibrium random field Ising model transition. So what you do is you take a random field Ising model system and you drive it quasi-statically with a source, and then you change the disorder strength so that you reach criticality. So this is the point of this transition. And there are some numerical works from early 2000s that have shown that the hysteresis and equilibrium transition exponents are very close numerically. And this is quite interesting, because there is no a priori reason why it should be so. And furthermore, we have an exact argument by Eisenman and Ware from 90s, which tells us that the equilibrium, that the lower critical dimension for this equilibrium case is 2. However, we have shown recently that classes of equivalence are different below the lower critical dimension. However, some exponent seems very close among other eta. So it's not clear whether what is the story about lower critical dimension. In this work, surely we cannot say anything about lower critical dimension. And there exists a certain amount of disagreement in the previous works about this. So there is a large-scale numerical simulation done by Spasojevic, Aničević, and Knežević from 2011, who say that there is a hysteresis transition in 2D. However, there is a recent study by Hayden, Raju, and Setna who say that there isn't a transition, because they use some new concepts of normal form theory, which allows them to filter out some contributions that might not be there but are visible numerically. Okay, so our concept of the boundary layer gives us a way to offer a low-lying answer to this question from the boundary layer analysis. First observation is that there is indeed a boundary layer behavior upon the approach to the lower critical dimension in the random field leasing model as well. And the flow of U is very similar to the pure leasing case. So basically, formally, it's the same, but the regulator is different and involves some exponents of field rescaling that are not present in the pure case. And what we find in the 2019 paper is that all flows of the RG functions for hysteresis can be written in the following form. So basically, we have a part which pertains to equilibrium. And to get hysteresis, you need to add certain number of anomalous terms. And what our boundary layer analysis tells us that the anomalous terms for all renormalization group functions are subleading in the boundary layer width, which leads us to the conclusion that the differences between the fixed point solutions and critical exponents and everything, they go to zero as the lower critical dimension is approached. So by the implication of the analytical result by Eisenman and Ware, we should claim that the hysteresis lower critical dimension is also 2. Okay, so here is the summary of the main points of my talk. I thank you all for your attention, and you can reach me either on my email, either on Slack or Remo. I'm going to be online. So thank you very much for the attention.
Okay, thank you very much. Okay, so now session is open for questions or comments. So please raise your hand if you have.
So,
oh, hello.
Yes,
can
please.
I?
Yes, please.
Hello,
Ciao, Ivan. So I wanted to ask you something that we were also discussing at some point. So you showed that your result at LPA prime for the anomalous dimension is very close to 1. Can I ask you, how did you do these computations? How you proceeded?
Yeah, so basically what happens is that you have the implicit form solution for C. And this gives you, so this together with the equation for the anomalous dimension eta, which you can obtain at LPA prime, this gives you all that you need to determine eta. And then you use the equality that epsilon is 0, which is d minus 2 plus eta is 0. And then you can express explicitly the lower critical dimension. But the fun part is, since you have this exact solution for this quantity that you need in eta, you have the analytical expression for it, then you can just insert it inside your equation for eta, and you get an analytical number, which is 2 pi minus 1 over pi plus 1. That's for the lithium regulator with the prefactor of 1. Okay. Okay,
because this, sorry, I see that there are no more questions, so I hope I can go on a bit, because I am a little bit puzzled, not puzzled. So as you know, I agree with your results, but quantitatively, we know that the anomalous dimension of the Ising, the expression that you get in LPA prime, it's pretty very overestimated. Because if you do the calculation in 2 dimensions with that definition, this will give you 0.4, which is almost 2 times the well-known exact result. So nothing. So basically this,
yeah,
I am not sure.
But there is a trick that I haven't shown because there's no time. So when you try to optimize, there isn't an optimum at LPA prime. But the fun part is that at second order, the optimum reappears. So
but it is below d equal 1.
No. This is the result. The DL that I showed. This is the result.
Okay, well, I should think to this a bit more. It's complicated.
Okay, I mean, we can discuss whether.
Yeah, for sure.
Thank you.
Okay, other questions or comments? Okay, if not, let's start to speak again.
Thank you.
Also, this is the end of the session, so let's thank all the speakers in this session. And is there any announcement from LOC? If not, let me mention that there is a remote session from 9. So please join and have discussion.
Oh, there is one more remote session, free discussion session from 6:30. It's already open. And because just after the normal Zoom session, it's better to have remote sessions. And I added the